These are solutions to assignment 4.2. If you haven't already, stop and watch the video on shadow problems, and then come back and try number 2 on your own first before you listen to me. All right, whenever the problem is a geometric problem, I would highly recommend making a diagram. And I hope you remember the idea of shadow problems from geometry. This is my lamppost. Not a very beautiful lamppost. And Sarah is walking away from the lamppost. So here's Sarah, and she is given to be 4 feet tall. So this point right here is Sarah's distance from the lamppost. So if she's walking, this point is going to be moving to the right. And since it's horizontal, I think I'll put X for the distance between Sarah and the lamppost. And Sarah's shadow at any point in time is going to be this black line. So this black line is the shadow. So I think I'll put S for shadow. And, well, let's see what we're given here. We are told how fast Sarah is moving away from the lamppost. So I would say that we are given dx dt. So the distance between Sarah and the lamppost is changing at 2 feet per second. What are we looking to find? How fast is the tip of the shadow moving? The tip of the shadow right here is also going to be moving to the right. So I think I could say that we're going to find ds dt, or another way you might set up this problem is to say, well, this bottom segment of the triangle, let's call that y. And that should work for you too. You could find dy dt. But of course, y is really the same as x plus s. So whether you call it y or whether you call it x plus s, we're going to be doing the same thing. So to come up with a model, we're looking for an equation that involves x and s. And what I see in this problem is similar triangles. Let's make sure everybody sees that. This green triangle is similar to the large red triangle. So by similar triangles, I would say that 4 in the green triangle corresponds to 10 in the red triangle, as S in the green triangle corresponds to x plus s. And you could call that y, but then I think you're going to end up changing it anyway in your next step. So I want an equation with x and s, and if I cross multiply in our proportion here, this is going to simplify to be a super easy problem. So I might even solve this for s. So 4 over 6 is 2/3 of x. So there's our static model. We haven't done any derivative yet. So now I want to differentiate with respect to time. And I think I'll scroll over here. So we'll have ds dt. And the derivative of 2/3 x is just 2/3, but then don't forget the chain rule on the x, dx dt. So our related rates model is simpler than in the previous problems. So ds dt is what we're looking for. And in our specific case, we don't have any x at all. So notice that the value of x doesn't matter. The value of x doesn't appear here. So the value of x doesn't matter. dx dt was given. That was how fast Sarah was walking, and that was 2. And so we'll come up with a simple, quick answer for ds dt of 4/3 feet per second. So regardless of how far Sarah is, no matter how far Sarah is from the lamppost, her shadow is going to grow at a rate of 4/3 feet per second when she is walking 2 feet per second. All right, let's move on. Snowball melting. So we are given a hint here by the formulas that we've got a spherical snowball. So its surface area is decreasing. So that's interesting that we are given not the change in the volume, but we're given the change in the surface area. So I would say we're given a dA dt. And it says that it's decreasing, so let's be careful to make this a negative rate. So it is decreasing at 1 cubic centimeter per minute. And our question says find the rate at which the diameter decreases. Well, that also is not expected. In our formula, we're usually expecting to use radius. So we could find the change in diameter with respect to time. Or you might say, could I find the change in radius first and then double it? Think why I would say that. If we know that this radius changes in this direction, then wouldn't the diameter change that amount in both directions? So shouldn't the change in diameter be twice the change in radius? So I think you could find either one of these to come up with your result. Okay, so let's use radius first, since that is what's in the formula. So if we find a formula that involves surface area and radius of a sphere, of course it's right here under our nose. The area of a sphere is 4 great circles, so 4 pi r squared. Differentiate with respect to time, so we'll do the power rule to get 8 pi r, and then the chain rule on the r, dr dt. So here's our related rates model. And now we can plug in any specific case that we're interested in. And here it says we're interested in the specific case when the diameter is 10. So let's not fall for that. We know that we want to switch here to radius. So let's make that a 5 for the radius. And we were told the dA dt was -1. So if we divide both sides by 40 pi, and then let's think about the units for our dr dt. So the change in radius should be in centimeters to the first power per minute. So if that's the change in our radius, then our theory is that we should be able to double it. So multiply by 2 and that would cancel into the denominator. So this is what I think our result should be for the change in diameter. So let's see if there was another method that would get us there a little more directly, and it would be your choice of which method you want here. So instead of using the formula with radius, could we rewrite it? Instead of r squared, what's another name for radius? How about d over 2? Isn't diameter over 2 the same thing? So look at how simple this formula would be. D squared over 4. And of course our 4's would cancel. So we've got an even easier formula to start out with. And we differentiate implicitly with respect to time. And change in diameter is what ddd is. The derivative of diameter with respect to time. And now we plug in our specific case. dA dt was the given. And now the diameter that we're interested in is 10 centimeters. And the dd dt is our variable. So let's divide both sides by 20 pi. And we see that we've got the answer we expected either way. So, of course, you don't have to do the problem twice. Here I use the formula using radius and then doubled our dr dt to get our dd dt. And here we change the formula first to use diameter. All right, one more problem. And a water tank. Let's get a diagram. If it's geometric, make a picture. So in this case, our cone has a base radius of 6 feet and a height of 12 feet. So notice that the radius is 1/2 of the height. And as it fills with water, so if I pick a specific height here, if this were filled with water, do you see that the blue triangle would be similar to the red triangle. So even in the blue triangle, the radius would still be 1/2 of the height. So it doesn't matter how much water is in the cone, the radius is always 1/2 of the height. All right, why is that going to help us? Well, it's going to reduce our number of variables. What's given? If the water level is falling, well, this is interesting. In the previous assignment, we were looking for the change in the height of the water. Here we're given that the water level is falling. So here we're told the dH dt, the change in the height of the water. And it is decreasing or falling, so we again have to make sure we use negatives. And I notice I'm going to write inches per minute here, and let's watch that carefully, because right below here I see 8 feet. So I want to make sure that I don't mix inches and feet together. All right, what are we looking for here? The question said, find how fast is the tank losing water. How fast is the tank losing water is the same as saying what's the volume of water that we're losing. So the rate at which we're losing volume. The rate at which we're losing volume is what we're looking for, dV dt. So we want a static formula for a cone that involves the height and the volume. And we know the volume is 1/3 the base area times the height. The base area is a circle, pi r squared. And we don't care about the radius. We only care about height and volume. So that's where this little trick of saying, hey, we can replace r, because we've already determined that the radius in this problem, not in every cone, but in this cone, the radius happens to be 1/2 of the height. And then we're going to square it. So our volume formula, if I square that, is going to be 1/4 h squared. So I'm going to use pi over 12 h cubed as our static formula. We still haven't done our calculus. So to get related rates, now I'm going to differentiate with respect to time. So we will have dV dt is equal to pi over 12. And then our h cubed, we're going to use the power rule, so 3h squared. And a chain rule, dH dt. And you can skip right to the next step. I hope some of you would have canceled the 3 with the 12 right away. So this is our related rates model. And now we can plug in any specific case that we're interested in. And the specific case says when the water is 8 feet deep. 8 feet deep, and we've got inches here, so I guess 8 feet. We better change this to 96 inches. 8 feet is 96 inches. So for our specific case, let's be careful about that. So we're going to keep the pi over 4. We're going to take the height of 96 inches squared, dH dt, and our dV dt was the one that was given. We were losing 2, nope, sorry, other way around. Change my mind. dV dt is what we're looking for. And dH dt was what was given to be -2. And as soon as I write that 96 squared, I think I am making a mistake here. I think I better go back and check all of the units. So do we want to use inches or do we want to use feet? So I'm going to back up a step here. And I think that we might want to. Here's why I'm changing my mind. Look at what we did here. We were in feet. The ratio, though, wouldn't make much difference. So whether you use inches or feet is really your choice. But let's make sure we're consistent. So if I'm going to use 8 feet here, I can either change the 8 feet to inches, which is what I was going to do a minute ago, or we can change the 2 inches per minute. So I think the 2 inches per minute could be just as easily written as -1/6 foot per minute, right? 2 inches is 1/6 of a foot. So I think maybe I'm going to do that instead of having the 96 inches. I don't want to square the 96, so that sounds like a good plan. So I'm going to try again. We're looking for dV dt. Our specific case has the height of the water at 8 feet. So I'm going to keep this in feet this time. So I'm not going to bother writing that. So h squared, and our dH dt, I'm now, instead of the 2 inches per minute, I'm going to convert that so it is also in feet per minute. I don't know. Do you want to see the units in here? So 8 feet, and we're going to square that. And the dH dt is -1/6 foot per minute to the first power. So here, let's do some arithmetic. And I want to make sure that as long as we're this far that we're seeing the units, and then we're multiplying by -1/6 feet per minute. So for sure, I wanted everybody to see where we get cubic feet per minute. The units fall into place as we expect. And we could do some canceling here. Let's go step by step. The 2 could go into the 64 to be a 32. And the 6 we could at least divide by 2. So this is now 16. So it looks like we will have a -16 pi over 3 cubic feet per minute. And I think that you can round these to decimals if you prefer. Make sure you keep at least 3 decimal places. But I think this exact answer looks fine. So that should do it.